Now on, we will study about the thermal performance of the fin. Okay, so recall from the last lectures, uh, we've been discussing that fins are attached on the base surfaces, and fins increases the heat transfer by increasing the surface area, right? So when we increase the fin, it increases the heat transfer area and hence heat transfer rate to the surrounding. However, when we are attaching the fin to the base, we are attaching actually the material, solid material, which itself poses thermal resistance, let's say L by Ka, to the material, to the base material, right? So fin itself poses the conduction resistance to heat transfer to the original surface, right? So for this reason there is no assurance, and we have to find some assurance criteria that heat transfer will really be increased or not if we put the fin on the base surface. All right, so for the assessment of this matter, we have to study some performance parameters of these fins. First one is fin effectiveness. So having said that, what is the scope of this thermal performance of the fins, so first let's define fin effectiveness. First of all, consider on this left hand side a base surface in which there is some source of heat which is generating the heat inside the base surface, and its temperature is high and we want to cool this base surface. All right, so when there is no fin attached to it, okay, for this particular area, and when fin is attached to it on the right hand side, as we can see, of length L in the same convection conditions. So here we are assuming in general, when we attach the fin to the base surface, convection coefficient changes, but for this analysis and in also in textbooks, it is assumed that when we attach the fin to the base surface, the convection coefficients are unchanged. All right, so when we are attaching to the base surface this fin of length L, so this is how the situation look like. All right, so when we attach the fin, so temperature at the base of this fin, all right, means the surface which is in contact with the base having the temperature T naught, and as we move along the length L of this fin, the temperature keep on decreasing, okay, and at some particular temperature TL at length L. All right, so this is the condition with the use of fin. And when there is no fin, base surface, this cross-sectional area, which is the cross-sectional area of the fin, is having temperature T naught, means every point on the surface is having temperature T naught. But for comparison and for definition of this fin effectiveness, we are considering only this surface, this cross-sectional area, which is the cross-sectional area of the fin, W times thickness, width times thickness. All right, so when there is no fin attached to the surface, so heat transfer from the base surface without fin for this particular area is H times cross-sectional area of the fin times theta naught. Theta naught means temperature drop, temperature difference between the base surface and the surrounding fluid. All right, T naught minus T infinity, and AC is width times thickness. All right, and for the right hand side case, when fin is attached to the surface, in general heat transfer from the whole fin is defined like this: heat transfer coefficient times the perimeter of the fin times the elemental distance dx along the length, and T, here T is variable as we can see, minus T infinity. So at every point there will be a difference of temperature, and this difference is not constant, so we need to integrate from 0 to L. All right. So we need to integrate this expression from 0 to L to get the heat transfer with fin. All right. So fin effectiveness is defined as the rate of heat transfer with fin and by the without rate of heat transfer without fin. So it is a ratio. So it is a ratio, non-dimensional number, which is heat transfer with the fin and heat transfer without fin. So for very long, so this expression on the numerator changes depending on the condition, right? Are we considering about the infinitely long fin or finite length fin? Finite length fin also has two cases, as we have seen previously, that if the fin tip surface is insulated or not, right? So for let's see for the very long fin case, for which heat transfer from the fin is defined like this: under root of h times p times k times AC times theta naught. Theta naught means base temperature minus the ambient fluid temperature. All right, here it is defined like that, and this expression we derived in the previous lectures. And without fin, it will be same for every type of fin. All right, because it is not dependent on the temperature profile of the fin. It is dependent wholly on the cross-sectional area of the fin, where it is attaching on the base surface, heat transfer coefficient, and the base surface temperature and the ambient fluid temperature. All right. So after simplifying this expression, theta naught will be cancelled, and simplifying we get under root of pk divided by HAC. All right. So this expression tells a lot of things about the effectiveness of the fin. All right. First, fins are effective when they will be made up of high thermal conductivity material, like you can see. So it is proportional to the thermal conductivity, square root of thermal conductivity. So with increasing the thermal conductivity of the material, effectiveness of the fin increases. Similarly, it is also inversely proportional to the heat transfer coefficient and also the cross-sectional area. All right. So here we can see that effectiveness is high when heat transfer coefficient is low, and where heat transfer coefficient is high, fins are less effective. Okay, so in general we should use the fins where resistance from the fluid is high. It means convection of that particular fluid is low. All right. So fluid side thermal resistance we have defined like 1 by h times area. So if h is low, thermal conductance resistance, thermal resistance will be high, right? So for example, fins are used in the automotive radiators on the air side, where air is blown, all right, and coolant is flown on the tubes, and outside we are having the triangular kind of fins on the automotive radiator where air is flowing. So that's why it means that air has less convection coefficient, so fins are used there to utilize their higher effectiveness. All right. And liquid side convection already high, but air side convection is low. It means resistance to heat flow is high. That's why to reduce that resistance, we are employing fins on the outside where air is flowing in the cross flow. This is a cross flow heat exchanger, which is automotive radiator. All right. And also from the above expression, fin effectiveness is inversely proportional to cross-sectional area of the fin. All right. So this cross-sectional area also contains the thickness. So if we have less thickness, we are having fins of wave fins are very effective. All right. So as a thumb rule, we should use thin fins and closely spaced, but not that much closely spaced that they will affect the flow of fluid between the two fins. Because if the flow is impeded by the spacing, then convection resistance will increase, and the sole objective of the use of fin will be discarded. Right. So we should use thin fins, thin, closely spaced fins in practice. Okay, they are preferred actually. Alright, next we will talk about, right now we have looked how to write the expression for the effectiveness for very infinite line, very long fin, or you can say infinite length fin case. But what about the finite length fin? Finite length fin also has two cases: fin tip is insulated and fin tip convection is considered. All right. So again, the effectiveness is defined like the same: heat transfer with fin and without fin, the ratio. And for fin with insulated tip, it is defined at under root hp KAC. H is heat transfer coefficient, P is parameter of the fin, K is thermal conductivity, cross sectional area, AC, and theta naught is the temperature drop, temperature difference, and tan hyperbolic of ml. All right. And for the fin with convection coefficient, convection is considered from the tip. For that case, the L is replaced in this expression as the corrected length. All right, we have seen that how to find this corrected length for the finite length fin with convection considered on from its tip. So it is L plus cross sectional area plus by parameter of the fin. All right. So this expression is giving us the dependence of the fin effectiveness on the length. We know that as we increase the ml, the tan hyperbolic is saturated. So as we increase from 0 to 5, tan hyperbolic value is saturated from 0 to 1. All right. So for a given m, as length is increased, effectiveness is increased. So as L increases, effectiveness increases, but up to certain limit. After that, it will saturate. All right. So we should not waste material beyond that particular length. Right. So it will be like this. So after this ml value, we should not add the material to the base surface as a fin, because it will add extra length with no added effectiveness. And also heat transfer from the fin will not increase after this particular ml value, and it is taken to be 2.65 in the literature. All right. And m is, we all know that m is nothing but under root hp by KAC. H is here ambient convection coefficient, and P and AC are depending on the geometry of the body, cross sectional area and parameter, and K is material property. So if they are constant, if we increase the length, effectiveness first will increase and it will saturate. All right. So in summary, for this fin effectiveness, for good fin performance,